So the results of the previous derivation we just discussed left us with a value for b, which is basically our earlier lowercase constant b applied for total kilocalories per day of 0.019 kilocalories per cubic centimeter of blood per day. Now, this differs from biologically determined results of how many kilocalories per day are needed to actually maintain blood levels and basically the function of the heart for which has been measured to be about 0.05 kilocalories per day per cubic centimeter of blood, of course, versus biologically determined. This is a pretty big difference on the order of 5/2 magnitude. And Murray actually discusses a second derivation that solves some of the problems inherent with the first one. So he goes to a second derivation where he assumes that the flow, F, and the surface area of a capillary or a vein or an artery S should be kept constant instead of flow and the length of the vein or capillary or artery. Now, this second derivation goes something like this. S, which we're now keeping constant instead of L, equals 2 pi, or pi, R, L, and volume equals R, S over 2. So our earlier equation, the equation for E, becomes E equals F squared S times 8 eta over 2 pi squared r to the 5th plus BRS over 2. Now this, again, we take the derivative of this with respect to r to find the optimal case, and we set that equal to 0. And then this becomes negative 5 F squared S times 8 eta over 2 pi squared r to the 6th plus BS over 2. And then solving for B, we have, let's see, BS over 2 equals 20 F squared S eta over pi squared r to the 5th y to the 6th, which implies that B equals 40 F squared eta over pi to the 6th, no, pi squared r to the sixth. Now, this new result gives us a value of b which is about 5/2 times our old result. So 5/2 times 0.019. Is about equal to 0.047 kilocalories per cubic centimeter day, which is much, much closer to biologically determined So as you can see, this result, although the only thing that changes is a factor of 5/2, gets us a much closer result to what we would expect biologically. Importantly, however, regardless of the method of derivation used to achieve a result for the value of b, both of them yield a surprising result in terms of the flow rate through a capillary or a vein or an artery, and the proportionality of the flow rate to radius. And we can see that by solving either equation for f, the flow rate. We'll use the first one here, where it works for either of them. And that result is that f equals r to the third times the square root of pi squared b over some constant times eta, which then leads to the result that flow is equals some constant k, we'll call the constant, times r cubed, or flow is proportional to r cubed. Well, this is an important result because the simplest form of this relationship can be expressed as Q, the volume flow we discussed earlier, of blood through an artery or a vein or a capillary or any sort of blood vessel in the circulatory system, is equal to K times r cubed. And this means that when we have branching of flow from a large vein or a large artery here to multiple smaller ones here and here to multiple even smaller ones, the flow has to maintain this relationship. And that relationship, because as we know, the flow linearly, the linear flow f goes by the cube of the radius, that k naught r cubed equals a times r1 cubed plus b times r2 cubed plus C times R3 cubed plus so on and so forth. Now, going back to our earlier derivation step, we can show that this constant, whether it's A, B, C, or K, is only comprised of the values B, remembering this was our earlier use of B when we said it was the cost to make blood, eta, and pi. Now, all of these are unchanging whether you're in a larger tube or a smaller tube, so the branching doesn't affect these. Therefore, we can say that the constant K is equal to the constant A, equal to B, equal to C, and so forth. All of these constants are equal. Therefore, the relationship between flow rates in a larger branch and smaller branches coming off of that larger branch goes as R0 cubed equals R1 cubed plus R2 cubed, and so on and so forth. Now that we've established this relationship, we can say that at any point in the circulatory system, when you're coming off of the aorta down to even the smallest capillary, if you add up the cube of the radius of all the capillaries, it will equal the cube of the radius of that initial branch.